Good day, students. We are welcome to an insightful series of our physics lesson that is going to kick off immediately. For now, we are going to start with scalars and vector. These lessons are specially packed to ensure the students get a headway when preparing for their O-levels and A-levels exam. So today we are starting with this topic in physics, scalars and vector, and I believe that by the end of the class, students will be able to appreciate everything that they need to learn from the topic. So scalars and vector is a very, very important topic in physics. One very, very important topic in physics because it apart from knowing the topic itself, the essence of the topic cuts across everything that is required in physics. For example, we are going to see it in several areas of physics. We are going to see it in friction. We are going to see it under equilibrium. We are going to see it even in electricity. When we are talking about electric field, we are going to see it. Now, we need to define scalar quantities and we need to define vector quantities and we need to see everything that is daring to be learned in the topic. Scalar quantities are quantities that do not have direction. They are quantities that have only magnitude but no direction. Magnitude and direction are two very important or key words in this particular definition. When we say magnitude, what do we mean by magnitude? Magnitude is the size, the amount of a quantity. When you attach number to a quantity, you know the magnitude. When I measure a quantity for you and I attach number to it, 5, 10, 15, 20, 80, that is the magnitude. Even age, the age of humans have magnitude. An 80-year-old is 5-year-old, 10-year-old, and 20-year-old. Those are the special numbers that we use to refer to our ages. It is the numbers that is attached to these quantities that help us to understand the size of the quantity when we speak to them in relative terms. Everybody understands that 80 is more than 20, and everyone understands that 5 is less than 10. So the parts of a quantity that help us to understand how big the quantity is what is called the magnitude, the size, the amount. So when a quantity has only magnitude, but it does not have direction, we call that type of a quantity scalar quantities. But when a quantity has both magnitude and direction, we call it vector quantities. So vector quantities are quantities that have both magnitude and direction, while scalar quantities are quantities that have only magnitude. As we can see from those definitions, we'll say that magnitude is one that is common to both quantities, but direction is one that is specific to only vector quantities. So we're talking about scalars and vectors. Essentially, what we are going to use to differentiate between the two of them is the direction. Now, when we talk about scalar quantities, those are quantities that have only magnitude but no direction. There are so many examples. In fact, those are the largest number of quantities that we have. We have, for example, I said it earlier, your age is a scalar quantity. If I ask you for your age, you tell me 16, 17, 18. You don't need to tell me 18 years eastward, 20 years southward, 55 years northward. You don't attach direction to your age. When you tell me the size, the amount, the magnitude, the number part of your age, that is all that I need. So your age is a scalar quantity. But there are so many other more technical quantities that are scalar in physics. Example, your length is a scalar quantity. The length from a point to another is a scalar quantity. If I ask you to measure the length of the space in your room, you tell me 5 meters, 3 meters, 10 meters. These are just magnitude. You don't need to attach direction. If I ask you to measure the length of your room, you tell me 5 meters. You don't need to attach 5 meters northward or 5 meters up or 5 meters down. So length is a scalar quantity. Time is a scalar quantity. Time does not have direction. Time, if you measure the time that it will take you to move from your house to the market or from your house to school, it is a scalar quantity. You don't need to attach direction to it. So length, we said it earlier, is a scalar quantity. Time is a scalar quantity. Electric current is a scalar quantity. Electric current is a scalar quantity. Your mass, how heavy you are, is a scalar quantity. If I ask you for your mass, you tell me, you report the answer back to me in kilogram. 10 kilogram, 20 kilogram, 5 kilogram. These are just magnitude. You don't need to attach direction to those quantities for me to understand how heavy or light you are. So your mass is also a scalar quantity, and there are so many other ones too. Temperature is a scalar quantity. Temperature is a scalar quantity. If you ask for the temperature of a body, it is usually reported with magnitude and magnitude alone. 2 degrees Celsius, 10 degrees Celsius, 20 degrees Celsius, these are magnitude values. You don't need to attach direction to temperature. And we are still going to see, as we continue in our study of physics along, how the other scalar quantities, and in fact, there are so many other quantities that you can also classify as scalar as we move on. Speed. Your speed is a scalar quantity. Your speed, how fast you are, is a scalar quantity. When you attach direction to speed, you don't call it speed anymore. You now call it velocity. We are going to see that when we get to motion. Essentially, that is the only difference between velocity and speed. When we refer to speed, the magnitude alone, we are talking about speed. But when we attach direction to speed, it becomes what we call velocity. So the man traveled 5 meters per second. That's just speed. The man traveled 5 meters per second northward. That is velocity. So essentially, the only difference between speed and velocity is that while one has a direction, that is velocity, the other does not have, that is speed. So that makes speed a scalar quantity and velocity a vector quantity. Now, there are other quantities that we refer to as vector. Those are the ones that have both magnitude and direction. Now, a very good example of vector quantity is force. In fact, force is so important as a vector quantity that most of the time, some physics students feel like force is the only vector quantity that we have, whereas there are still so many other vector quantities. Force is a very good example of one. Velocity is another example. Momentum is another example. Momentum is another example of a vector quantity. There are still several other examples of vector quantities that we are still going to refer to in the course of this study. So we have vector quantities, we have scalar quantities. I said vector quantities are quantities that have vector quantities are quantities that have both magnitude and direction, while scalar quantities are quantities that have only magnitude but do not have direction. So we are going to move on in our study of scalars and vector. How do we combine scalars and vector quantities? How do we get to combine scalars and vector quantities? Scalar quantities are combined normally. If I bring a scalar and I bring a similar scalar quantity to it, I'll just combine it normally by either adding or subtracting. If, for example, the length of the space of your room is 2 meters and I ask you to increase it by 1, then it means we are going to move from 2 to 3. So what I did there was just to add 2 to 1. But if the length in your room is 2 meters, the length of the space in your room is 2 meters, and I ask you to reduce it by 1, then what we will have in essence is 2 minus 1, which is 1. So this is done easily because scalar quantities are just either added or subtracted anytime we need to combine them. If your body temperature is 20 degrees Celsius, for example, and after some bout of malaria, the temperature rises by 5 degrees Celsius, then it means the final temperature becomes 20 plus 5, which is 25. If it reduces by 5, it means 20 minus 5, which is 15. So it is easy for us to combine scalar quantity. Amount of money is also scalar quantity. If you have 1,000 naira and after some spending spree, you are able to spend 200 out of that 1,000, the simple answer is just 800. That is what you'll be left with. But if you have 1,000 naira and somebody comes around to give you additional 300 naira, it means what you will now have is 1,300 naira. So we combine scalar quantity by just adding and subtracting them. Vector quantities are not that simple to combine. Vector quantities are not that easy to combine. There are some part of vector quantities that requires very simple combination, but there are some other parts of vector quantities that if you need to add them together, you must have to do some you must have to apply some mathematical principles as regards how to solve triangles and so on. So those are the things we want to look at. But first, how do we represent vector quantities? Number one, how do we represent scalar quantities? We don't even need to represent scalar quantities because they don't have direction. But vector quantities are usually represented with a line that has an arrow. Vector quantities are usually represented by lines that have arrows. The arrows show the direction in them, and the line, the length of the line, shows their magnitude. For example, if I represent a vector quantity this way, and I represent another this way, what I'm indirectly trying to tell you is that both of them have the same direction, but one seems to be bigger than the others. One has a greater magnitude than the other. That is why I've represented this with a short line, and that is why I've represented this with a very big line. In more absolute representation of vector, the length of that line, you have to draw these things to scale. The length of that line might have to represent the size or the magnitude of that vector. If I represent a vector this way, and I represent another this way, what I'm indirectly telling you is that one is in the direction, in this direction, while the other is also in this direction. One is, I can say that one is in the right direction, is rightward, while the other one is southward or downward. So there are so many ways by which you can represent vector, but essentially we use a line that has an arrow to represent vector. Now, in representing vector, how do we combine when we have more than a vector? If, for example, I have a vector, let me pick a very good example, a force. I told you earlier that a force is an example of a vector. A force of 7 Newton and another force of 3 Newton. And this time, I want you to combine them. When you combine vectors, what you are getting is called the resultant vector. Anytime you combine vectors together, what you are getting is called the resultant vector. And I'm going to define that for you. The resultant vector is that single vector which will have the same effect in magnitude and direction as all the other vectors acting together. For example, if 7 and 3 Newton are to be exerted on an object, if somebody comes to you and pull or push you with a force of 7 Newton, and that person comes to push or pull in the same direction with a force of 3 Newton, we can say that now you have two forces exerted upon you. We can also say that you have two vectors, because forces are examples of vectors. We have two vectors exerted on you. Now, there is a particular vector that I can use to replace those two vectors. There's a particular vector that I can use to replace those two vectors that will do the same thing that those two vectors will do. There's an effect that 7 and 3 acting on you simultaneously will create. There's a particular vector or force that will create that same effect, such that I don't really need to use two vectors on you. I will just use one that will still do the same thing that 7 and 3 will do. That vector, if I'm able to find it, is what I'm calling the resultant vector. Resultant is from the English word results. It's like saying that what will 7 and 3 result to? What would be the result of 7 and 3 acting together? So I will define it again. I said the resultant vector is that single vector which will have the same effect in magnitude and direction as all the other vectors combined or acting together. Now, mind you, I must also remind you that it is not just two vectors that you can find the resultant. You can find the resultant of any number of vectors. If you have 10 vectors, if you have 5 vectors, if you have 16 vectors acting on an object, I can ask you to find the resultant of all 16, all 5, all 10. The resultant remains that single vector. It has to be one that will do the same thing that all the other vectors acting together will do. Now, how do we determine the resultant of vectors? We are going to start by treating the determination of resultant anytime we have two vectors. Then from there, we'll move on to the determination of resultant when we have more than two vectors. So for now, we are going to get busy with the determination of resultant vector when we have only two vectors acting on an object. Now, determination of resultant. For two vectors, the method we are going to apply depends on how the two vectors are represented relative to each other. The resultant of two vectors depends on how the vectors are represented relative to each other. The simplest form of determination of resultant is if the two vectors are in the same direction. If the two vectors are in the same direction, we simply add to get the resultant. We'll do a simple addition to get the resultant. A very good example. If I have 7 Newton acting in the eastward direction, and I have 5 Newton acting in that same eastern direction. 7 Newton, 5 Newton acting towards the east. And I ask you to find the resultant of the two. The resultant will be obtained by just doing a simple addition of the two vectors. So the resultant of 7 and 5 acting in the same direction is just 7 plus 5 Newton, and the answer will be what? 12 Newton. So if an object is exerted upon by 7 Newton and 5 Newton forces, the effect they will create, as long as this 7 and 5 are in the same direction, will be the same effect that 12 will create. So 12 Newton acting in their direction will simply replace 7 and 5 acting in the same direction. So anytime vectors are in the same direction, don't forget, we get their resultant by a simple addition. And the resultant that we get will also be in their original direction. You know, the original direction here is to the east, but our 7 Newton is towards the east. Our 5 is also towards the east. The resultant we are going to get will also be towards the east, and that is 12 Newton. I hope that is very clear. We move on to the second. When the vectors are acting in opposite direction. When the vectors are acting in opposite direction, I'm still going to use my original example, though this can be extended for any vector or any magnitude that is given to you. Let us assume that I have 7 Newton acting westward, 5 Newton acting eastward, and I wish to find the resultant. Here, they are acting in opposite direction. They are clearly acting in opposite direction. So how do I get the resultant when vectors are acting in opposite direction? I'll get the resultant by doing a simple subtraction of the two. So the resultant here is going to be 7 minus 5. And 7 minus 5 is 2 Newton. It is not like here when they were in the same direction and we added to get the resultant. Here they are in opposite direction and we are now subtracting to get the resultant. So the resultant of 7 and 5 acting in opposite direction is 2 Newton. But that is not all. Anytime we are getting the resultant, we must get resultant in both magnitude and direction. Here, the magnitude of my resultant is 12. The direction of my resultant is towards the east. Why? Because the two original vectors that I was given are also acting eastward. So the resultant I'm going to get, since they are in the same direction, will also share that same direction with them. Now, if I have 7 Newton acting towards the west and 5 Newton acting towards the east, the resultant of the two will be obtained by a simple subtraction. And we have done that already. It is 7 minus 5, which is 2. What direction will that 2 be? The 2, which is our resultant, will be in the direction of the force that is greater. It will be in the direction of the vector that is greater. The vector that is greater here is 7. 7 is greater than 5. So the resultant I'm going to get will be in the direction of 7. And the direction of 7 from this example that they gave me is west. So the direction of my 2 will also be towards the west. So don't forget that when vectors are in opposite direction, we get them by doing a simple subtraction, and whatever we get as a resultant must be in the direction of the vector that is greater in magnitude. So I wish to also revise, there are instances where you can be given vectors that are in the same direction, but the question will not clearly state that they are in the same direction. There are instances where you can be given vectors that are in opposite direction, but the question will not explicitly state it that they are in opposite direction. There are other things I can give you that will suggest that they are either in the same direction or in opposite direction. Anytime you are told that vectors are inclined at 0 degrees to each other, anytime that you are told that the vectors are inclined at 0 degrees to each other, it means they are in the same direction. Anytime we are told that vectors are acting at 0 degrees to each other, it means they are in the same direction. Anytime we are told that vectors are acting at 180 degrees to each other, it means that they are in opposite direction. And mathematically, that makes a lot of sense. When vectors are in opposite direction, we can see that the two of them forms a straight line, and we know clearly that the angle on a straight line is 180 degrees. Anytime vectors lines are making 0 degrees to each other, it means they are parallel and they are in the same direction. So if I want to give you vectors and I want to tell you that they are in the same direction, but I don't want to clearly state that they are in the same direction, I will tell you that they are inclined at 0 degrees to each other. That way, you should know that they are in the same direction. Similarly, if you are told that vectors are at 180 degrees to each other, it means that they are in opposite direction. So we've done same direction. We've determined the vectors for same direction. We've determined the resultant of vectors for opposite direction too. So we want to look at when the vectors are perpendicular to each other. When the vectors are perpendicular to each other, being perpendicular means they are making 90 degrees with each other. When the vectors are making 90 degrees with each other, how do we determine the resultant? We have treated 0 degrees to each other. We have treated 180 degrees to each other. We want to check what will be the resultant when they are at 90 degrees to each other, and how would that be? Number one, let me try to represent any two vectors that I know are at 90 degrees to each other. Sometimes you'll be told that they are at 90 degrees to each other. Sometimes it is the direction that they gave you in the question that will suggest that they are at 90 degrees to each other. For example, if I have 7 Newton in the direction of the north and I have 5 Newton in the direction of the east, 7 Newton towards the north, 5 Newton towards the east, clearly these are at 90 degrees to each other. But how did I know that? We know that there are 4 cardinal points. We learned that long ago. The direction of the north, this is the direction of the south, the left is your west, and the right is your east. Because this is a point, we are drawing the 4 cardinal points through a point. We understand that angle at a point is 360 from mathematics. Now you have divided that 360 into 4 parts. We have divided the 360 degrees into 4 parts. Each of those parts is called a quadrant. Quadrant is a fourth of a cycle. Now, if we find the fourth of this angle, we'll get 90 degrees. So this has to be 90 degrees. This has to be 90 degrees. This has to be 90 degrees. And this has to be 90 degrees. So there are a pair of directions that it will give you on the cardinal plane that will suggest that the angles are at 90 degrees, or the direction are at 90 degrees to each other. For example, if you are given north and east, that's 90. East and south, that's also 90. South and west, that's 90. West and north, that is 90. Now, so we are taking one of such. Let us assume that we are giving 7 Newton in the north direction. We are giving 5 Newton in the east direction. Now we want to find the resultant of the two. So I can ask you to find the resultant of 7 and 5. when they are at 0 degrees to each other. I can ask you to find the resultant of 7 and 5 when they are at 180 degrees to each other. Now, I want you to find the resultant of 7 and 5, that same 7 and 5 when they are at 90 degrees to each other. What do we do? Clearly, what most students will naturally do here is just to complete the shape as a right angle triangle. Is to complete the shape as a right angle triangle, then they will find that diagonal or the hypotenuse as the resultant. While that will give them the magnitude, it will not appropriately give them the direction. So I will not suggest that you use this type of method. I will suggest that you draw the resultant in the exact direction that the resultant should be. Now, how do we continue that? I will not use this to determine my resultant. While that will give me a quick answer if I need the magnitude, it will not give me a very correct answer when direction of the resultant is important. And like I told you earlier, anytime you have to find the resultant, you have to find it in both magnitude and direction, because those are the two components that makes a resultant vector up. Because vectors generally have magnitude and they have direction. So what I will do in this case is I'll draw my 7 Newton and 5 Newton. I will turn this shape to a rectangle. I will turn it to a rectangle. How will I do that? By making a copy of this 7 and putting it on this other side. I don't need to put the arrow because that is just a copy of the original vector given to me. I will make another copy of this 5. I'll put it here. So this is 7 and this is 5. Clearly that becomes a rectangle. The actual resultant that you need is not the one that you have drawn earlier. It is the one that comes from their point of intersection. The resultant of a pair of vectors must also come from their point of intersection. The resultant of a pair of vectors must come from their point of intersection. If this is 7 and this is 5, this is their point of intersection. So when you draw your resultant this way, you can see clearly that that is wrong because it's not coming from the point of intersection of 7 and 5. Point of intersection is a point where 7 and 5 meet. That is this point. So anytime you want to get the resultant of two vectors, particularly when they are at angles other than 0 and 180 to each other, you must draw it from their point of intersection. So after making this up into a rectangle, it becomes easy for me to just draw that resultant from their point of intersection. That diagonal drawn from their point of intersection is the resultant that I want to find. And it's going to give me the magnitude of that resultant correctly. It's going to also give me the direction of that resultant correctly. Now, how do we find that? We can simply use our Socatua. Remember that the angle here is 90, and because it is a rectangle, we expect all the other angles in the shape to be 90 degrees. Each and every one of those angles should still be 90 degrees. Now I want to find the resultant. To get the resultant, it is still going to be the hypotenuse of 7 and 5. If I pick this triangle, this resultant will be the hypotenuse of 5 and 7. If I pick this other triangle, it will be the hypotenuse of 7 and 5. So the resultant is the hypotenuse using any triangle that you have, because now that we have drawn the diagonal, the rectangle has been divided into 2. So now I want to determine the resultant. Clearly, we'll use our Pythagorean formula. That's hypotenuse squared is equal to opposite squared plus adjacent squared. So the hypotenuse in this case is the resultant that I'm looking for. The opposite in this case is 7 squared, and the adjacent in this case is 5 squared. Since I don't have any angle, r squared is equal to 7 squared is 49 plus 5 squared is 25. R squared becomes, if I add 49 to 25, we'll have 74. R becomes square root of 74. The square root of 74 is 8.60. 8.60 Newton is going to be the resultant for this question. the resultant in magnitude. When we solve a value this way to get the size, we have only been able to get the magnitude part of it. Mind you, I said earlier that the resultant is in two parts. There is a magnitude and there is a direction. Now I want to find the direction. I'll go to the point of intersection of the original vectors and the resultant vector. I'll go there to look for the angle. I can either find the angle that this resultant is making with 7 or the angle that the resultant is making with 5. This is the angle between the resultant and 7, and this is the angle between the resultant and 5. I can find anyone. But for the sake of notations and bearing, it is good that we determine the resultant with the north. There are two major cardinals. There are two cardinals that can be referred to as major cardinals here. That is your north and the south. That is why when you study your bearing notation form, you discover that most of the time they always start with either the north or south. And they will give you the angle, then they will end with either the east or west. So bearing like this are commonplace: south 10 degree west, north 55 degree east, and so on and so forth. They always start with the south or the north, and they always end with west or east. So with that, I would like to call the north and the south the major cardinal. If I have a choice of determination of two different angles, I would rather find the one that the resultant is making with either the north or the south, because those are what I refer to as the major cardinals. So I can find this, let me call it theta. I can find that angle theta. So if I need to find theta, it becomes tan theta is equal to the opposite of theta in this triangle is 5. The adjacent of theta in this triangle is 7. The hypotenuse is, mind you, the resultant that I've been able to find. But for now, I don't need that hypotenuse. So I can do tan theta is equal to 5 all over 7. Theta becomes arctan of 5 all over 7. And arctan of 5 all over 7 becomes 35.54 degrees. That is the value of our theta from the calculation. So now we can express it. We can express our resultant, therefore, as 8.60 Newton, acting at not 35.54 degree east. Why did I express it this way? Because it is between the north and the east. The answer that I have is between the north and the east. That is all. That is how to determine the resultant when two vectors are perpendicular to each other. If two vectors are perpendicular to each other, it means they are at 90 degrees to each other. So the next thing is you complete the rectangle for it, and you determine the diagonal that is drawn from their point of intersection. Once you can find the diagonal that is drawn from their point of intersection, that is the resultant. In determining the diagonal from their point of intersection, all you need to do is just do a simple application of Pythagorean theorem and use your trigonometry ratio, either sine, tan, cos. But tan is always better because it will give you the value that you're expecting in terms of the original quantities that the question is given to you. So that is all about that. So the next that we'll move on to for the determination of resultant of two vectors is we have treated resultant of vectors that are at 0 degrees to each other. We have treated the resultant of vectors that are at 180 degrees to each other. We have also just treated the resultant of vectors that are at 90 degrees to each other. We now want to check, what if they are inclined at each other at angles other than 90? If they are inclined at each other at angles other than 90, for example, if two vectors are inclined at each other at 60 degrees, if they are inclined at each other at 120 degrees, if they are inclined at each other at 200 degrees, they can be inclined at each other at any angle between 0 to 360. It is possible that they are inclined at each other at even 200, 300 degrees. Before we move on, I want to talk about how we represent them when they are at angles other than 90, 0, and 180, the ones we have just done for. We understand from our basic mathematics that there are different types of angles. Some angles are called acute angles. Some angles are called obtuse angle. Some angles are called reflex angle. Of course, we have a right angle that is 90 degrees. I won't talk about that because we have just finished solving about 90. What type of angles do we call acute? Acute angles are angles that are between 0, they are greater than 0, but they are less than 90. Angles from 0 to anywhere less than 90 is called acute angle. For obtuse, obtuse angles are angles that are greater than 90, but they are less than 180. For reflex, reflex angles are angles that are greater than 180, but they are less than 360. So, two vectors can be inclined to each other at any of these angles. And it is very important that we know how to draw them, because that will help us to understand how we are going to draw the resultant. Number one, when two vectors are at acute angles to each other, for example, we have two vectors, let me give you A and B this time. If they are at acute angle to each other, we tend to draw them like this, if the angle is acute. A very good example of acute angle, 45 degrees, a very good example of acute angle. Any value between here, 0, and less than 90, this is how we represent it. This is how we represent angles that are acute. What if they are obtuse angle? What if they are inclined at obtuse angle to each other? If they are inclined at obtuse angle to each other, we tend to represent them like this. We tend to represent them with the vectors opening up more than they were when they were having just acute angle between them. So we tend to represent obtuse angle this way. Obtuse angle, a very good example of obtuse angle that I can pick here is, let's say, 160 degrees. 160 degrees is an obtuse angle, and we tend to represent them this way. What about reflex? Reflex are those ones that are at 180. When we represent acute this way, we represent right angle this way. It looks like this other edge of the pair is opening up. When it is still like this, it is acute. When it is of this form, we call it right angle. It has opened up to 90. When we keep opening, we get to a point where it now goes beyond 90. Then at that point, we represent it as obtuse. It's obtuse. If we open it a little bit further, we will have a straight line, and that is 180. If we keep opening in that same direction, we'll get something that looks like this. So this is reflex. Once it goes beyond what we can refer to as 180, once it opens beyond a straight line, then it becomes reflex. And a very good example of reflex, like 200 degrees is a reflex angle, 300 degrees is a reflex angle. In fact, if it opens further, it is still reflex. If I have 300, it opens further. So if two vectors are at a reflex angle to each other, I will prefer to draw them this way. I'll draw them either this way, if they are still less than 270, or this way, if they are greater than, if the angle between them is greater than 270. So for example, a very good example is 200 degrees. If we have a vector A and a vector B at 200 degrees to each other, I want you to draw them this way. If we have a vector A and a vector B at 300 degrees to each other, I want you to draw it this way. Now, if we call this acute representation of vector, we'll call this obtuse representation of vector, I'll call this other two the reflex representation of vector. It simply means that when we look at it very well, if two vectors form reflex angle on one side, they must form either acute or obtuse on their reverse side. If two vectors form a reflex angle on one side, they must form either acute or obtuse on their reverse side. How is that possible? Remember that the total angle at a point is taken to be 360. If the angle at a point is taken to be 360 and a part of it is 200, it means the other side, if I subtract it from 360, will just be 160 degrees. And 160 is an example of obtuse angle. If two vectors are 300 degrees to each other and the sum of angle at a point is 360, it means on the inner side, we'll have 60 degrees. That is, how did I get 60 degrees? 360 minus 300. So that becomes the angle on the reverse side. That is why I said that when two vectors form reflex angle, they will also either form acute or obtuse on their reverse side. So we are going to treat acute, how to determine the resultant of two vectors when they are inclined at acute angle to each other. We are going to treat obtuse, when the resultant of two vectors, when they are inclined at obtuse angle to each other. But we are not going to really treat reflex, because in treating these two, we will definitely have treated reflex, because reflex, like I said, also form either acute or obtuse with each other on the reverse side, and that is what we are just going to use. So when we get to reflex, I'll just tell you what you need to do to turn the question into either of these two that we are going to treat. Now, how do we determine the resultant of two vectors when they are inclined at an acute angle to each other? We are going to use a very important law in physics to do that. That law is called the parallelogram law of vector. That law is called the parallelogram law of vector. What do we use parallelogram law of vector to do? We use parallelogram law of vector to determine the resultant of two vectors when they are inclined at any angle to each other. When they are inclined at any angle to each other, specifically when they are inclined at acute or obtuse angle to each other. And we are going to see that very soon. So in determining the resultant of two vectors inclined at any angle to other than 90, 180, or 0 to each other, we are going to need the parallelogram law of vector. The parallelogram law of vector, from the name parallelogram, which is a very common quadrilateral in mathematics. And we are going to use so many features of that quadrilateral in this class. Now, let me state the parallelogram law of vector. We are going to see it on the screen. The parallelogram law of vector states that if two vectors are represented in magnitude and direction by the adjacent sides of a parallelogram, if two vectors are represented by the adjacent sides of a parallelogram, then the diagonal drawn from their point of intersection represents the resultant vector in magnitude and direction. I'll go over that again. If two vectors are represented in magnitude and direction by the adjacent sides of a parallelogram, then the diagonal drawn from their point of intersection represent the resultant vector in magnitude and direction. How do we apply it? I'm still going to continue with my original vector 7 Newton and 5 Newton. Now inclined to each other at an angle of, let's say, 60 degrees. Don't ask me how I was able to draw it like this. I told you that once they are inclined at acute angle, this is how we draw them. The very first thing is we'll try to make this look like a parallelogram. We'll try to make this look like a parallelogram. And how are we going to make this look like a parallelogram? We are going to apply the same method that I did for when two vectors are at 90 degrees to each other earlier. We are going to make a copy of each of the vector and put it on its opposite side, the way it is. I'm going to make a copy of 7 Newton and I'm going to put it on the opposite side. 7 Newton. I'm going to make a copy of this 5, the way it is. I'm going to put it on the other side. You may not need to put the arrow, so that you will differentiate the copied vector from the original vector. This 7 is the copied vector, the original vector is 7 Newton. 5 Newton is the original vector. I've been able to make a copy and put it on the reverse side. If you have done it very well, then you should get a parallelogram. What is a parallelogram in mathematics? A parallelogram is a quadrilateral, number 1. It has 4 sides, that is why it's a quadrilateral. It has 2 pairs of opposite sides that are also parallel and equal in length. This side is equal in length to this side. They are opposite, they are equal. Apart from just being equal, they are also parallel to each other. That means when you extend them, either upward or downward, they will never meet. This side and this side are also equal in length to each other. Apart from being equal in length to each other, they are also parallel to each other. That means when you extend them in their direction, they will never meet. So a parallelogram has 2 pairs of opposite, parallel, equal sides. Now, anytime we have this, we have a parallelogram. So when you go back to my representation of the 2 vectors, 7 Newton is copied on the other side as 7 Newton. So being 7 and 7, they are equal in length. And since I've been able to get the exact way of inclination of that 7, it means they are also going to be parallel to each other. And 5 and 5 are also parallel to each other. And since I've been able to get the exact way, they are also going to be parallel to each other. Now they are equal in length too. So we have been able to fulfill the first part of that law. And what is the first part of that law? The part that says that if two vectors are represented in magnitude and direction by the adjacent sides of a parallelogram. I have turned these 2 vectors, 7 and 5, into the adjacent side of a parallelogram. What do we call adjacent? And if any 2 sides that you pick in a parallelogram will either be adjacent to each other or opposite. If they are not opposite, then they are adjacent. Opposite means they are directly facing each other. If this is side A, this is side B, this is side C, this is side D. A and C are opposite to each other because they are facing each other. B and D are opposite to each other because they are facing each other. And that is all. Those are the pairs that are opposite to each other. Any other pairs that you pick from that parallelogram will not be opposite to each other. Instead, they will be parallel to each other. They will be adjacent to each other. Adjacent means they are side by side. If you sit adjacent to a person, it means you are sitting beside the person. So as you see here, A and D are beside each other, so they are adjacent to each other. D and C are beside each other, so they are adjacent to each other. C and B are also beside each other, so they are adjacent to each other. The same thing with B and A. So when you check what we have done here too, you will discover that at any 2, 5 and 7 that you pick, any pair of 5 and 7 that you pick will be adjacent to each other. This 7 and 5 adjacent, this 5 and 7 adjacent, this 7 and 5 adjacent, this 5 and 7 adjacent. So the first part of that law has been fulfilled, which states that if 2 vectors, 7 and 5, are represented in magnitude and direction by the adjacent sides of a parallelogram. So I've been able to represent them by the adjacent sides of a parallelogram. So now the next part, then the diagonal that is drawn from their point of intersection. Mind you, this is the point of intersection of the original vectors. The diagonal that is drawn from this point, we know the diagonal. All quadrilaterals have 2 diagonals. This is a diagonal, and this is a diagonal. Even rectangle, square, any quadrilateral that you pick must definitely have 2 diagonals. This is a diagonal, this is a diagonal, this is a diagonal, this is another diagonal. Now, the diagonal that is drawn from their point of intersection, is the resultant vector that you are looking for in magnitude and direction. So I'll go over the law again. It states that if 2 vectors are represented by the adjacent sides of a parallelogram in magnitude and direction. Then the diagonal drawn from their point of intersection represents the resultant vector in magnitude and direction. So that is clear to understand and that is clear to apply. It is not rocket science for you to be able to represent two vectors, no matter how they look. Even if they are inclined at obtuse angle to each other, all I just need to do is I'll pick this, I'll put it here. I'll pick this, I'll put it here too. It looks like a quadrilateral. If they are at any other, let us assume they are of this form. All I need to do is, if this is A and this is B, I will make a copy of A, I'll put it on the opposite side. I'll make a copy of B, I'll put it on the opposite side. So that makes it a parallelogram. So what I need to do clearly is to find this resultant. I must be able to find this resultant. If I can get it, that is the resultant. This line, that is the resultant that I'm looking for. Now we'll take a course to talk about what is required for you to find that aspect of the parallelogram, that part of the parallelogram. Meanwhile, I must let you understand that the physics in this has actually ended. What you now need to complete this question is mathematics. You must be able to solve. The last time we were solving vectors at 90 degrees to each other, we used Pythagoras theorem and we used trigonometry because those are two methods that are available for us to solve for sides and angle in a right angle triangle. When you have other angles apart from right angle triangle, or you have other angles apart from right angle, the triangle you're also going to get is not going to be a right angle triangle. So you must have your method in mathematics that you can use to solve for triangles that are not right angle triangle. And usually what we do, we don't use Pythagoras theorem, we don't use SOHCAHTOA. What we use instead are what we call sine rule and cosine rule. So I'm just going to briefly run through that so that by the time I try to apply it, it will not look like we did not talk about it. So when we have a triangle, any triangle of any form, the very first thing you must know or you must do to that triangle is you must be able to name that triangle precisely, correctly. How will I name this triangle correctly? The very first part of a triangle that I want you to learn how to name is the angles. Usually, it is a standard in mathematics that we use capital letters to name the angles of a triangle. So if I can call this angle A, I can call this angle B, and I can call this angle C. It's not compulsory that there's a particular point that is fixed to A. I can start from here too. I can call this A, B, C. I can call it P, Q, R. I can call it X, Y, Z. But it's good to use capital letters to name the angle. So this is an angle A, this is your angle B, and this is your angle C. If you name the angle, it is the angles that will help you name the sides. For example, if this is angle A, his side is the side that is directly facing it. The side of that triangle that is directly facing it is the side of that A. So this becomes side A, and for the side, I'm using small letter. If this is angle B, his side is the angle that is directly facing it. So this becomes the side B, and I'm using small letter. If this is angle C, the side that is directly facing it is side C, and I'm using small letter to represent that side. So that is side C. So that is generally how to name a triangle. I will take one more example so that we understand what we're trying to do here. If I have a triangle, the very first thing is to name the angles. Name the angles. Name your angles. So I'm going to name this angle angle P. I'm going to name this angle angle Q. I'm going to name this angle angle R. So if that is the case, then I will do the naming of the side. The side of R is the side that is facing it. The side of P is the side that is directly opposite to it. And the side of Q is the side that is directly opposite to it. That is side Q. So if you can name your triangle, then you are on course to trying to solve it using the methods that I talked about earlier, sine rule and cosine rule. Now, if I can name the triangle correctly, all I just need to do is now to write the sine rule or the cosine rule. Sine rule, cosine rule are usually written for the sides. If this is side A and I want to determine it, it must be A squared is equal to B squared plus C squared. I'll first write a part that makes it look as if I was going to write the Pythagoras theorem, but I'll have to continue. Minus 2, then I'm going to use this to BC, cos the only angle I will use is the angle of A, cos A. So generally, when you check cosine rule, you are starting with the same letter that you are ending with. Only that while you are starting with the angle of that letter, while you are starting with the side of that letter, you are ending with the angle of that letter. And if that is the case, I can also write that cosine rule for B. If I want to write it for B, it becomes B squared is equal to the other two sides. That's A squared plus C squared minus 2AC cos the angle of this that I'm starting with, B. I can also write it for C. If I wish to write it for C, it becomes C squared is equal to the other two sides, A squared plus B squared minus 2, then this and this, AB, cos the angle of what you have started with, the angle of C. And quite simply, this is what we call the cosine rule. And the cosine rule is one of the methods that we can use to solve for a triangle that is not a right angle triangle. Once we've done that, we can now also apply sine rule. For sine rule, that one looks a little bit more easy to use. A all over sine A must be equal to B all over sine B, and that must be equal to C all over sine C. We'll pick any two that applies to what we need and what you have been given. If I've been given the whole of A, I know the side A and the angle A, and I've just been asked to find either the side or angle B when I'm given the other, then I just pick A and B parts. So you don't need to write the three together. So I'm going to come back to my problem. So when I use this later, please understand that this cosine rule and sine rule are what I can use to solve for triangles, sides and angles of a triangle when the triangle is not a right angle triangle. One other thing I need to also talk about before we move into the solution of that resultant is the features of a parallelogram. I had earlier told you that a parallelogram has two pairs of opposite, equal, parallel sides. Two pairs of opposite, equal, parallel sides. That's a parallelogram. Now, there's another thing with a parallelogram. A parallelogram requires that you are given only one angle. While a parallelogram has 4 different angles, you need to be given only one to find the other 3. A parallelogram requires that you be given only one angle to find the other 3. If, for example, I've been given this angle to be 30 degrees, then with that, I can find the other 3 angles. Why? The adjacent angles of a parallelogram are supplementary. When angles are supplementary, it means when we add them together, they give us 180. When angles are supplementary, when we add them together, it gives us 180. So adjacent angles, angles that are side by side, are supplementary. If this is 30, the side beside it has to be 150. How did I get that? When we add them together, 150 is the angle that when you add to 30, you get 180. And because this is 150, and I said that adjacent angles of a parallelogram are supplementary, it means if this is 150, this must also be 30, because when you add them together, they must give you 180. If this is 30, this must be 150. When you add them together, it must be 30. It must be 180. So you see that because I've been given 30, I was able to find the other 3 angles. So similarly, if we are given any other angle, then we can find the other 3. Now, I want to do that same thing here. For this problem, I'm going to apply what I just told you. If this is 60, the adjacent angle to it must be 120 in the parallelogram. Why? When you add them together, they must give you 180. If this is 180, if this is 120, this must also be 60. Why? When you add them together, they must be 180. And if this is 60, this must be 120. When you add them together, they must be 180. So with it, I think I should be able to solve that triangle now. I can now pick any of the triangles that I have by drawing the diagonal. I can pick the one down, I can pick the one above. So I'll prefer to pick probably the one down. If I do that, I'm going to have this. So of these two triangles, I've been able to extract one out. It's the same thing that you are going to get and if you had pulled the one on top. So this is 5, this is 7, this is 120. I hope you know that this is no longer 60 because the diagonal has cut this 60 into 2. The two of them will not be equal except if the vectors are the same. The only thing that will make this diagonal to divide the angle at the point of intersection into 2 equal parts is if these two vectors are the same. And since they are not the same, we don't expect it to divide it equally. So we don't need it because we have another angle that we can easily use, which is 120. Now I can name that triangle and I'll proceed to using cosine rule to solve the problem. So I'll name it. Remember how I said you should name a triangle. This will be side A, angle A, sorry. This will be angle B, and this will be angle C. If that is the case, then we can now say that, okay, the sides, this is side A, side C, this is side B, and this side that is opposite to our A is side A. Mind you, based on what I told you earlier, we are looking for the diagonal. That's the resultant. The diagonal in this case is what is represented by side B. So I need to find out side B. I can write the cosine rule for side B. It becomes B squared is equal to A squared plus C squared minus 2AC cos B. If that is the case, we can now slot in our values. B squared is equal to A. Our A in this case is 7 plus C squared, 5 squared, minus 2 times A is 7 times C, 5, cos B. Cos B is 120. So I can continue with that. B squared is equal to 49 plus 25 minus 2 times 7 is 14. 14 times 5 is 70. So we are multiplying that with cos 120, and cos 120 in this case is 0.5. So if we continue with our cos 120 is minus 0.5. We'll continue with our simplification. We have B squared is equal to, if we add these two, that will be 74. We'll multiply minus with minus. That will give us plus. 70 times 0.5 is 35. So we have B squared. We'll continue our solution is equal to 109. That's the addition of 74 and 35. B becomes square root of 109. And square root of 109 is 10.44. That's the square root. So we'll put 10.44 Newton. That is the magnitude of our resultant. 10.44 Newton is the magnitude of our resultant. Now, remember that I said resultant comes in 2 parts. There's a magnitude and there's a direction. So now I'm going to start with the direction. The direction can be found as angle. In this case, we find the direction as an angle. You can either find the angle if this is the resultant and it is our resultant. We can either find the angle between the resultant and 5, or the angle between the resultant and 7. The angle between the resultant and 5, or the angle between the resultant and 7. So you can find it. Even while we were solving for the vectors inclined at 90 degrees, we found the angle between the resultant and one of the two other vectors. So now I'm going to find the resultant, the angle between the resultant 10.44 that I now have, and either 5 or 7. I wish to find the angle between 10.44 and 5. You can also find the angle between it and 7. If I know this angle, I can use angles in a triangle to get this. Now, it's so easy to do. How will I solve that? I can now use sine rule. Usually for problems like this, you don't need to solve resultant. You don't need to solve using cosine rule twice. Once you use cosine rule the first time, you can use sine rule the other time. So that becomes A all over sine A is equal to B all over sine B. What is our A from this problem? It is 7 all over sine. What is angle A? Our angle A is the angle that we are looking for. Must be equal to B. Our B in this case has just been found to be 10.44 side B all over sine. Our B in this case is 120, sine 120. So we can continue and solve the problem. If we do that, we will have 7 all over sine A is equal to 10.44 all over sine 120 is 0.866. So we can cross multiply and make sine A the subject of the formula. If we do that, we'll have sine A will be 7 times 0.866 divided by 10.44. I'll find the arcsine of that. If we do the arcsine of that, arcsine of 0.7866, 7 times 0.866 divided by 10.44, we'll have our A to be 35.50 degrees is our answer. So we'll say that the resultant for this problem, is clearly going to be, our resultant for this problem is going to have a magnitude of 10.44 Newton, and it is inclined at 35.50 degrees to the 5 Newton, force. So that is how we determine the resultant when the vectors are inclined at angles other than 90 degrees to each other. The very first thing, we draw them, and we'll make sure we draw them correctly. The next thing is we use parallelogram law of vector, 1, to complete it and make it look like a parallelogram. 2, we draw the required resultant as a diagonal, the precise diagonal that we need. Then we'll bring out one of the two triangles that we obtained, then we'll solve it using cosine rule and sine rule. And by then we should have the answer to the resultant when the vectors are not at 90 degrees to each other. So we'll move on from there. I'll just explain this, of course, is for acute angle. I'll just explain for obtuse and reflex. Obtuse and reflex. How do we do for obtuse and reflex? For obtuse and reflex, we will do when two vectors are inclined at obtuse angle to each other. Let's say 7 and 5 inclined at 150 degrees to each other. It's still the same process that we are going to repeat. We'll make a copy of this 7. The way it is, we'll put it on its opposite side. Then we'll make a copy of 5. The way it is, we'll put it on the opposite side. And we should have a parallelogram. And with that parallelogram, then we can find the other angles. This angle will be 30 degrees. Because I said that adjacent angles must be supplementary. They must add up to give you 180. If this is 30, this should be 150. If this is 150, this should be 30. So any two adjacent sides that you pick must be supplementary. They must add up to be 180 degrees. Then we'll come to the point of intersection of the original vector. The point of intersection of the original vector, we draw the resultant. We draw the diagonal. That is the resultant that we are looking for. So with this, we can bring out one of the two triangles. We can bring out this triangle. If we bring it out, we have something that looks like 30. Mind you, since you have made a copy of this 7, this is where it will be. If you have made a copy of this 5, this is how it will be. So if this is 30, this is 7, and this is 5, then this is the resultant that I'm looking for. I can easily find it. So how do we represent for reflex 2? If we have 7, the very first thing is to draw the representation correctly. If two of them are inclined at 300 degrees, if they are inclined at 300 degrees, let's say this is 5 Newton and this is 7 Newton, what you just need to do is, I told you earlier that if they have a reflex angle on one side, they must have an acute angle or obtuse angle on the opposite side. So if the total angle at a point is 360, then this will be 60 degrees. If it is 60, I can continue with that, and it looks very much like what we have just done. I'm going to copy this 7. I'm going to put it on this other side. I'm going to copy 5 and put it on this other side, 5. Then I can easily find the resultant. The resultant is the diagonal that comes from their point of intersection. It's a resultant that will come from their point of intersection. And that should be what we are going to have. So, one thing I want you to observe, now that we have been able to determine the resultant of two vectors when they are inclined at any angle to each other, is the range of values that we have. The range of values that we have. Now, when two vectors are inclined at any angle, I hope you were able to see from the example that we have just done that there is a maximum value they can give you for their resultant, and there is also a minimum value that they can give you for their resultant. They can now give you any value between their maximum and their minimum based on the angle of inclination between them. For example, when two vectors are acting in the same direction, I said we'll get their resultant by a simple addition of the two vectors. That addition, that sum of the two vectors, is the largest resultant that two vectors can ever give you. For example, the example of 7 and 5 that we have just done, the largest resultant that 7 and 5 can ever give you is 12. It is not possible that 7 and 5 gives you a resultant that will be more than 12. 7 and 5 can only give you a resultant, the maximum resultant that 7 and 5 or any two vectors can give you is their sum. If I have a vector A and I have another vector B, the largest resultant that A and B can give is A plus B. And when will they give you A plus B? When they are in the same direction. Remember, I told you that the only time we get to add two vectors as their sum is when they are in the same direction. The smallest resultant that two vectors can ever give you is their difference. The smallest resultant that two vectors can ever give you is their difference. And when will you get their difference as their resultant? When they are in opposite direction. When two vectors are in opposite direction, their difference becomes their resultant, and that is the least resultant that they can give you. The example of 5 and 7 that we have just done, if I ask you, from 5 and 7, what's the maximum resultant that they can give you? The answer is 12. That's the maximum. I can now proceed by asking you, when will they give you a resultant of 12? When they are in the same direction. If I ask you, what's the least resultant that 7 and 5 can ever give you? It's 2. And when will they give you that 2? When they are in opposite direction, because that is when we get to subtract them. I can now proceed by saying, will 7 and 5, can they ever give you a resultant of 7? The answer is yes. Anything between their maximum and their minimum can be obtained as their resultant. The only thing now is what will be their angle of inclination. But anything outside their maximum and minimum, they cannot give you as a resultant. For example, 5 and 7 can never give you a resultant of 1. It's not possible. Why is that so? Because they are, the smallest resultant they can give is 2, their difference, and 1 is less than their difference. They cannot give you 1. If I ask you, can 5 and 7 give you a resultant of 15? The answer is no. 15 is more than the maximum resultant that the two of them can give. And what's that maximum resultant that they can give? The maximum resultant they can give is 12. They are sum. So by just looking at 2 questions, by just looking at 2 vectors, we should know the possible range of value that we expect the resultant of the 2 to be. It must be whatever answer you are getting for the resultant of 2 vectors, no matter the angle between them, must lie between their maximum and their minimum. It must not be less than their minimum. It must not be greater than their maximum. And I told you when they will give you those 2 vectors. Now, it is possible at times in some question that you will be given the resultant and you will now be asked to find the angle between them that will make you get those type of resultant. For example, I can ask you, what will be the angle of inclination? The angle of inclination between 7 and 5 Newton for you to obtain a resultant of 10 Newton. What must be the angle of inclination? What must be the angle between 7 and 5 before you can obtain a resultant of 10 Newton? Simply, what you just need to do is you go back to your parallelogram law of vector, represent your 7, represent your 5. This time we are not even giving theta, so we don't even know if it is acute, obtuse, or reflex. But you can just draw it anyhow for now. So if the angle between them is theta, complete this shape. So we'll complete the parallelogram as seen on the board. The angle of inclination is the angle between 7 and 5, and that's theta. Using what we know about a parallelogram, that supplementary angles are adjacent angles are supplementary if they are inclined at theta, and we have so completed their parallelogram the way it is, it means this angle has to be 180 minus theta. And if this is the case, it means this must be theta, and it also means this must be 180 minus theta. If that is the case, then we can draw the resultant from their point of intersection. This is the resultant drawn from their point of intersection. That resultant is 10 Newton. If that resultant is to be 10 Newton, then we can now bring out our one of the triangle. Remember that what we're used to is that the question will give us the angle, then we'll get the resultant. But in this case, we have been given the magnitude of the resultant, and we're asked to find the angle. In both cases, it is still cosine rule that we are going to use to solve our problem. I'll bring out one of the triangle. If I do so, this must be 180 minus theta. This must be 5, and this must be 10. This must be 7, and this is 10 from the triangle. So I can name the triangle. If I do so, I can call this angle angle A. I'll call this angle angle B. I'll call this angle angle C. If this is angle A, the opposite side is small side A. The opposite side to B is small side B, while the opposite side to C is small side C. If that is the case, then we can now write our equation for B, because B has what we are looking for. What we are looking for is theta, and theta, as represented on the board, can only be obtained from B. So I will write my equation in terms of B. That makes B squared must be equal to A squared plus C squared minus 2AC cos B.
If that is the case, b squared is 10 squared is equal to our a squared is 7 squared plus c squared 5 squared minus 2 multiplied by 7 multiplied by 5 cos b. If that is the case, we can continue. 10 squared is 100, 7 squared is 49, 5 squared is 25, minus 70 for the multiplication of all of this cos b. Our b is 180 minus theta. Our b is 180 minus theta. So we have 100 is equal to, if we add these two together, we should have something that looks like 74 minus 70 cos 180 minus theta. Then we can make our 70 cos 180 minus theta the subject of the formula. I can bring the whole of this to this other side while I take 100 to the other side. So I will have 70 cos 180 minus theta is equal to 74 minus 100. If that is the case, I can continue by simply saying that 70 cos 180 minus theta is equal to minus 26. How did I get that? 74 minus 100 is minus 26. I can continue with the evaluation. Cos 180 minus theta is equal to minus 26 all over 70. It's possible that you get negative in your expression of cos. You can get negative, you can get positive, and both angles are actually pointing at one particular value for you. You must not discard that negative. You must not discard that negative. So we have cos 180 minus theta must be equal to minus 26 all over 70. Will give us 26 divided by 70 is 0.3714. So what we are left with is for me to find 180 minus theta and get the arc cos of minus 0.3714. Arc cos of minus 0.3714. Of course, because it has a negative, that value cannot reside in the first quadrant. Mathematically, if your cos is negative, it cannot be in the first quadrant, because in the first quadrant, 0 to 90, the cos is positive. It can only be within the second quadrant, and we have some calculator that can give you the value directly, while there are so many other calculators that will require that you find the equivalent angle within 0 to 90. Then you can now use your knowledge of trigonometric ratio in all other quadrants to convert it back to the angle that it should be. So let us check. So that should be 111.8. That's what I have here as the inverse cos of minus 0.3714. So if that is the case, I can now complete it by determining theta. If I do so, theta must be equal to 180 minus 111.8, and theta must now be equal to 180 minus 111.8, 68.2 degrees. It means that if 5 and 7 are inclined at an angle of 68.2 degrees, they must give you a resultant that is equal to 10. They must give you a resultant that is equal to 10 based on what we have just saw. So cosine rule or parallelogram law of vector using cosine rule can be applied for situation where you need to get the resultant when you have been given the angle of inclination between two known vectors. It can also be used to obtain the angle of inclination between two known vectors if the resultant is given. That means if you give me the resultant, I'll give you the angle. If you give me the angle, I can also give you the resultant. So either of the two, you are going to use parallelogram law of vector, and you are going to ultimately use cosine rule to solve for whichever the question what you want you to find. Now we can continue. So we've been able to find the resultant of two vectors at any angle of inclination to each other. They are inclined. We started by treating they are inclined at 0 degrees to each other, if they are inclined at 180 degrees to each other, if they are inclined at 90 degrees to each other, if they are inclined at any other angle apart from what I've stated to each other, we use parallelogram law of vector, and quite easily we have been able to do that. We want to continue with the resultant, but this time we want to treat the resultant of more than two vectors. If I have more than two vectors, how will I find their resultant? If I have more than two vectors, how will I find their resultant? Very, very simple. What we have just solved for is for problems where we have only two vectors. But if we have more than two vectors, how do we find the resultant? Number one, the very first thing to do before we get to that point is to do what is called resolution. Is to resolve a vector. We have to do what is called resolution. We must resolve a vector. What does resolution mean? When you are resolving a vector, you are breaking it into component parts. You are breaking the vector into parts in the direction that is preferred for you to solve the problem at hand. If you take a vector and you break it into the direction that is preferred for you to solve that question, then you are doing the resolution. You are resolving a vector. Generally, we can have different type of vector considering the direction. I can have a vector that is horizontal. Horizontal means it is either to the left or to the right. I can have a vector that is vertical. Vertical means it is either upward or downward. I can have a vector that is now not horizontal and it is also not vertical. In that case, I will just use the word inclined. We can have a vector that is inclined. We can have a vector that is inclined either in this direction, in this direction, in this direction, or in this direction. Now, if I decide that I want a vertical vector, I want to solve problems on vector using the vertical axis, then it means if I'm given this type of a problem, the vectors are already in vertical direction. These vectors are already in horizontal direction. These vectors are not in horizontal and they are not in vertical direction. The reason why I'm talking about horizontal and vertical is these are the common directions that we always understand. These are the common directions that we have been made to understand right from even mathematics. If you want to draw your graph in mathematics, your lines on the graph are delineated on vertical axis and horizontal axis. Now, horizontal and vertical axis are the most common axes that we use. But that does not mean that they are the only set of axes that we have. There are so many other axes that we can make use of, or so many other directions that we can make use of apart from just horizontal and vertical directions. Now, inclined. If a vector is horizontal, I will accept that it is horizontal. If it is vertical, then I will accept it is vertical. But if it is inclined, it is not horizontal and it is also not vertical. If a vector is not horizontal and it is not vertical, I will say it is inclined. Such vectors can be broken down into horizontal and vertical components. Such vectors can be broken down to look like this horizontal and this vertical. if I break an inclined vector into two parts, that will make a part horizontal and another part vertical, what I am doing is called resolution. I'm doing the resolution of that vector. And there are so many ways by which I can resolve a vector. When you resolve a vector and you have been able to get the components in each part, then you can now use whatever you have obtained to solve the question along those parts that you have been able to get its components. The component of a vector is the effective direction, the effective value of that vector in that direction. The component of a vector is its effective value in that particular direction. If I take a vector that is 5 Newton, and I ask you to break it, to resolve it along the x and y direction, I'm saying that you should get me the component of that vector along the x and y direction. The component along y is the value of this vector along y. Its component along x is its value along x. That is why I define the component of a vector in any direction as the effective value of that vector in that particular direction. How do we find the component of a vector? To get the component of a vector, you must know the magnitude of that vector. For example, if this is a force and its magnitude is 5 Newton, I know the magnitude. I must also know the direction of that vector. How can I get the direction? Usually, they can either give us the angle that this vector is making with the horizontal axis or the angle that it is making with the vertical axis. The angle is making with the horizontal axis or the angle is making with the vertical axis. Either of the two, we can use either of the two to resolve. If I am given the angle that it is making with the horizontal, I will just draw from the point where that vector is drawn from. I will draw the horizontal axis beside it and I will indicate the angle. I will just indicate the angle. Let us assume that the angle is 30 degrees. What I am telling you now, when you see something like this, is there's a vector whose magnitude is 5 Newton and it is inclined at 30 degrees to the horizontal. There are times they can give me an inclined vector that is inclined to the vertical. It can be inclined to the vertical. If it is inclined to the vertical, this is the vector. Let's say its magnitude is 10 Newton and it is inclined at 60 degrees to the vertical. This is what I will do. They can even give me a vector that is inclined with any of your cardinal points. I can be given a vector that is 7 Newton in a direction north 15 degrees west. How will I represent this? I will draw my cardinal point. I will make sure that I know those two cardinals that they are talking about, north and west, the two directions they are talking about. Then from the point of intersection of those two directions, I'm going to draw my vector. They said the vector here is 7 Newton. If it is 7 Newton, I'll put 7 Newton, and it is at an angle of 15 degrees to the north, towards the east. You always show the angle to the major cardinal. It's good you show the angle to the major cardinal. When you are giving bearing angles in bearing form, you must show it to the major cardinal. So those are the representation. We can now be asked to resolve each of these vectors. Quite simply, to resolve a vector, without wasting much of our time, if I want to resolve a vector, what I will do is, from the point where the vector is starting, I will draw a vertical component beside it, and I will draw an horizontal component beside it. From that same point. All must start from that same point. The original vector you are trying to resolve, the horizontal part, and the vertical part. I'm not going to refer to them as part anymore. I'm going to refer to them as components. So if I can find this and I can find this, then I've been able to find the components of this 10. And once I know the component of 10, I've been able to resolve the vector. One simple way by which I tell my students to resolve is that the component of a vector in any direction, the component of a vector in any direction is the magnitude of that vector cos the angle between the vector and that direction. The component of a vector is the magnitude of the vector cos the angle between that vector and that direction. If, for example, I have a vector that is in let us assume that I've been given a vector 10 Newton and is making an angle of 60 degrees in a direction. It's making an angle of 60 degrees in a direction. Then the component of this vector 10 in this direction, I'm going to draw it from that same point and I'll put arrow on it because the component of a vector is also a vector. The component of this vector in this direction is the magnitude of that vector 10 cos the angle between the vector and the direction, which is what, 60. So 10 cos 60 is the component of 10 in this direction, or the horizontal component of 10, because that direction is an horizontal direction. I can continue. For this problem, if they ask me to find the horizontal component or the component of this 5 in this direction, which is the horizontal direction, it will be the magnitude 5 cos 30 degrees. I can even be given a vector and an arbitrary direction, a direction that is not even x or is not even y, does not look like x, does not look like y at all. What will be the component of this vector in this direction? The simple thing I need to do is, from that same point, I need to know the angle that the vector is making with the direction that they want. This is the vector, and this is the direction. Let us assume that the angle that is making with that direction is 45 degrees. And I also need to know the magnitude of that vector, let's say 8 Newton. The component of this 8 in this direction, therefore, will be 8 cos 45. 8 cos 45. The component of a vector in any direction is the magnitude of the vector cos the angle between that vector and that direction. So by extension, I can say that a vector will not have a component in the direction that is at 90 degrees to it. A vector will not have a component in the direction that is at 90 degrees to it. How? If I have a vector and there's a particular direction, that direction is now making 90 degrees with the vector. Let's say the vector is 7 Newton. That vector 7 Newton is making angle of 90 degrees with the vector. And I want to now find the component of this 7 in this direction. Let me draw the component first. And let me now use what I used here to determine the component, what I can use to determine the component to also find this component in that direction. I said the component of a vector in any direction is the magnitude of that vector, 7, cos the angle between that vector and that direction, in this case 90. If you check from your calculator, you will observe that cos 90 is equal to 0, and that will be 0. So a vector will have components in all directions except the direction that is at 90 degrees to it. A vector will have components in all directions, but it will not have components in the direction that is at 90 degrees to it. Because by the time you find this component in the direction that is at 90 degrees to it, it becomes 0, whatever the magnitude of that vector is. By extension, therefore, I can say that any vector that is vertical will not have an horizontal component. Why? That horizontal is at 90 degrees to the vertical. I can also say that any vector that is horizontal will not have a vertical component. Why? Because both of them are at 90 degrees. It is now not limited to only horizontal and vertical. You can extend it to any two directions, any two arbitrary directions that are not even horizontal and vertical. If I give you a direction this way, and I give you a vector this way, and I indicate that the angle between them is 90 degrees. And I ask you to find, let me assume that this vector has a magnitude of 15. I ask you to find the component of this 15 in this direction. Quite simply, the component will be 15 cos 90. The component of a vector in any direction is that vector cos the angle that is making with the direction. And 15 cos 90, remember I told you earlier that cos 90 is 0. 15 times 0 is equal to 0. So a vector will not have components in any direction that is at 90 degrees to it, but it will have components in any other direction. And all you need to do is just do the vector, and in some questions, I can even be given arbitrary values. I can be given values that are not even numerical. I can be given the vector to be A, and I can be given the angle between the vector and this direction to be theta. If I need to find the component of A in this direction, all I need to do is the magnitude, that is A, cos the angle between that vector and this direction, that's theta. A cos theta will do the job for me. Now, if you have a vector, let's say 10 Newton, we are given the angle, let's say 30 degrees. We can resolve this vector in the horizontal direction. I just told you the component of a vector in any direction is that vector, the magnitude of the vector, cos the angle that it is making with the vector or with the direction. But there's another thing that can be done. You can also resolve the vector in a direction that is making 90 degrees with it. What I'm saying in essence is this. If we have two different directions, and the directions are making 90 degrees between themselves, a very good example is the y and x axis. The angle between y and x axis is 90 degrees. Now, if we have a vector that is inclined between them, 10, and that 10 is making an angle of 30 degrees, as I said earlier with the last example, is making an angle of 30 degrees with the x-axis. The component on x, the component of that vector on x is 10 cos 30. The component of the vector on y will be 10 sin 30. So this that I've done will help you understand that you can actually resolve a vector in the direction that is at an angle to it and another direction that is at 90 degrees to that direction. X and Y are at 90 degrees to each other. So if I can find the component of that vector on X, I can also find its component on Y, because Y and X are at 90 degrees to each other. If cos is giving me one component, sine will give me the other component. And I can do this not just for X and Y alone. I can do it for any two directions that are at 90 degrees to each other. If I have an arbitrary direction, let's say direction A, and another direction, let's say direction B, and I have a vector between them, that vector is now making 50 degrees with A, but A and B are at 90 degrees to each other. So the vector, let's say the vector is 8 Newton. I can find the component of 8 on A. I can also find the component of 8 on B. I can find the component of 8 on A, and that will be 8 cos 50. Why? Because I told you that the component of a vector in any direction is that vector, the magnitude of the vector cos the angle that is making with that direction. Now, if I know its component on a direction, I can also know its component on another direction that is making 90 degrees with the first direction. B is making 90 degrees with A. If its component on A is cos, its component on B will be sine. So the component of this 8 on B will be sine 8 sine 50. That's what I'm saying. So I can therefore resolve a vector along y and x provided I have the angle between the vector and either of x and y. I'm going to do that with two different examples. Let's say this is a vector 15 Newton, and this vector is making an angle of 30 degrees with the horizontal. Then I have another vector. That vector is 8 Newton. That 8 is making an angle of 60 degrees with y. And I have asked you to resolve these vectors into their vertical and horizontal components. Vertical and horizontal components. What you will do quite simply is you will draw the horizontal. Make sure you are drawing both components from the point where the vector is originating and its vertical component. I will draw the two beside it. The component beside the angle, as we have said before, is cos. 15 cos 30. The other component in the direction that is at 90 degrees with the first, the other component will be 15 sine 30. So if they ask me to resolve a vector along y and x, that is simply what I will do. The component beside the angle will give you will resolve it by taking the cos. The other component will be sine. So once you resolve a vector into its vertical and horizontal component, you literally don't need that vector again. You can clean it out. And once you do this, you have resolved that vector. You don't have the vector anymore. What you have are the components of the vector. Along y, which is the y component, along x, which is the x component. If I ask you for the x component of that vector is 15 cos 30. If I ask for the y component of that vector is 15 sine 30. Let's do the same thing here too. We want to resolve this vector into its vertical and horizontal component. From the point where the vector is originating, please draw its y. From that same point, please draw its x. Now let us resolve it. The component beside the angle, the component that you have beside the angle here is the y component. So that becomes cos 8 cos 60. The other component is 8 sine 60. Once you do that, you don't need the original vector and its angle anymore. You can just clean it for the sake of simplicity. So these are the components of the vector. So when you wish to resolve a vector along x and y, all you just need to do is make sure that you know the angle that that vector is making with either y or x. And once you know that, the component beside the angle is cos, the other component is sine. There are some of us that might have learned it that x is always cos, the x component is always cos, and the y component is always sine. That is not always true. What is cos is the component that you have beside the angle. If the angle that is given to you is the angle that that vector is making with y, then it is the y component that will carry the cos. The other component will be what? Sine. If the angle that you have is the angle that that vector is making with x, then it is the x component that will be the cos. The y component in that case will be sine. So don't learn it as x is always cos. X can also be sine depending on where the angle is. But what we have just said is if there is a component, if there's a vector you are trying to resolve, the component beside the angle will be a cos theta because it's the one beside the angle. The other component will be a sine theta. In this case, if it is a vector b, the vector b is making theta, is making an angle of theta with the horizontal component. So the horizontal will be b cos theta, while the other component will be what? B sine theta. And that is what you should stick to. This is always better. Now, so what you are doing is called resolution. When you are breaking a vector into parts, into its component parts, then you are resolving the vector. You are resolving the vector. When you resolve a vector, you will get the component, and I've already defined the component to you. I said the component of a vector is its effective direction, in its effective value in that direction. So that is it. How can this component now help us to be able to find other things about the vector? Remember where we left off, we said we want to find the resultant of more than two vectors. We have three vectors now, we want to find their resultant. How do we find the resultant of more than two vectors? Let me give you some set of vectors and want to find the resultant. Now, if I'm given 8 Newton at 120 degrees, if I'm given 7 Newton or 6 Newton at north 30 degree east, I'm giving 10 Newton at 0, 0, 0. Then I'm giving 12 Newton at south 45 degree east. These are the vectors that we have. And the question is that I should find the resultant of this vector. Obviously, number one, I cannot use all the methods that we have outlined for finding the resultant of just two vectors. I can't use parallelogram law of vector in this question. It's not possible. I cannot also use Pythagoras theorem. I cannot use Socrates. I may get to use all of those ones later, but those ones are methods that can only be used for only two vectors. Here we have 4 vectors. There's 8 Newton, there's 6 Newton, there's 10 Newton, and there's 12 Newton. So I have 4 vectors. I have to find a way to draw it. That's the very first thing. When you have a set of vectors that you want to find their resultant, you draw them so that you have a graphic understanding of what you are talking about, of what you want to do. Now, in this question, I've been able to give you series of angles that they can use to express the direction of the vector. You can be given angles in 3-digit form. You can also be given angles in cardinal form. In this case, I'm giving angles in 3-digit form, just as the first one. Here, I'm giving angles in cardinal form. We must be able to draw angles regardless of how the question chooses to express them. Now, of course, either way, I expect you to have seen this one from mathematics, how we should be able to express it, we should be able to draw it the way we want. I hope you know that I said it earlier, angles that are expressed in bearing from, this is north, this is south, this is west, and this is your east. If it is given as northeast, then the vector is somewhere here. If it is given as southeast, it's somewhere here. If it is given as southwest, it's somewhere here. If it is given as northwest, it is somewhere here. So with all of those ones, I can easily pick what to do. It is also necessary to know that if angles are given in 3-digit form, we are to start clockwise from here, from the north. If they are given in 3-digit form, we are to start clockwise from the north. So if the angle, this point becomes our 0, once we cover the first quadrant, this place becomes 90. If we cover the second quadrant, it becomes 180. If it covers the next quadrant, it becomes 270, sorry. If it covers the next quadrant, it becomes 360. 360 is exactly at the same point where you have 0. So if I'm giving an angle like 150, 150 is between 90 and 180, then it should be somewhere here that they're talking about. If I'm giving an angle like 240, 240 is between 270 and 180, so it should be somewhere here. If I'm giving an angle like 60 degrees, 60 degrees is between 0 and 90, it should be here. If I'm giving an angle like 300, then it should be here, because 300 is between 270 and 360. Then I must be able to indicate those angles correctly as given with those values. Now I'm going to start with the very first one. The very first angle is 8 Newton at 120 degrees to each other. 120 degrees, mind you, is in 3-digit form. So I'm going to start clockwise from the north. From here to here is 90. From here to this point is 180. So 120 should be between the two. And mind you, whatever angle they give you in 3-digit form, you are measuring from the north clockwise. Whatever angle they give you in 3-digit form, you are measuring clockwise from the north. So I expect you to know that it is from here to this other point that is 120 degrees. So if that is the case, I don't always advise students to show the obtuse angle. I advise students to show
those angles, whatever the form they are given, in acute form. Acute form are always better to resolve than obtuse angle. But that still does not mean that you cannot resolve obtuse angle. We are still going to get to questions where we are required to resolve with obtuse angle, and we'll get to see how to do that. For now, if from this point to this point is 120, then I expect you to know that from here to here is 90. To this point, from this point to this point is 90. So if I'm going to indicate the remaining part, which is my acute angle, it should be 120, which is from here to here. I'm going to subtract the angle, the first quadrant angle from it. So I'll be left with 30. What I have done to get that 30 is I have done 120 minus 90. I've cut out this first 90 part from that expression to get that. So the magnitude of that vector is 8 Newton. So I've represented the first part. The second one, I'm also going to represent it. I have 6 Newton at north, 30 degrees. That is easy. This is north, this is my east. 30 degree east should be 30 degrees east should be here. 30 degrees east should be here. It should be between the north and the east. The magnitude is 6 Newton. 30 degrees means I'm going to show it with the north because I told you earlier the north is a major cardinal. Any angle that you have to show between the north and the east must be on the north. Now, that is that. The next one is 10 Newton at 0, 0, 0. 10 Newton at 0, 0, 0. I'm going to do 10 Newton at 0, 0, 0. What would that be? 10 Newton at 0, 0, 0 will be 0, 0, 0 in 3-digit form is exactly at this point. It has not even moved an inch away from the north. 10 Newton, I'm going to express it. 10 Newton at 0, 0, that's 10 Newton. For the sake of some clarity, I want to change this to west so that I will have another angle on the other side of the quadrant. I want to change this to the west. Now, so that I will solve 12 Newton as south, 45 degree west. This is my south. This is my west. I wish to indicate 12 Newton in this direction, 12 Newton between the south and the west. 45 degrees, I'm going to show my 45 with the south because south is a major cardinal. I'm going to indicate my vector. The vector's magnitude is 12 Newton, and that is it. That is all that I have to represent. So I have clearly represented all of these vectors in this direction. I've represented them on the board the way they are. And I hope we understand the way I've represented this vector. So we can now find their resultants. How many vectors do we have in the diagram? We have 4 vectors. So what are the methods that are available for us to represent each of these vectors? To find the resultant of each of these vectors, we will use a resolution. We will resolve them. That is why we have to first go through resolution of vector before we can now find this, before we can now touch how to find the resultant of this vector. And how do we do so? The very first thing you have to do is you will isolate each of these vectors. You will bring each of them out with the angle they are either making with the vertical or the angle they are making with the horizontal. You are going to isolate each one of them with the angle they are making with the vertical or the angle that they are making with the horizontal, either of the two. I'm going to start with 10. 10 Newton is vertical, completely vertical, 10 Newton. In that direction. I don't need to show any angle because it's already on the vertical. 6 Newton is inclined at an angle of 30 degrees with the vertical. The angle between 6 and the vertical is given. This is 6 Newton. It's making 30 degrees with the north. This is the direction of the north. Regardless of whether we have a force on the north or we don't have any force on the north, this is still the north direction. And the angle between that north and the 6 is 30 degrees. So we isolate it and bring it out that way. Then the next thing is we draw the 8 Newton. 8 Newton. Let's go and check the angle that 8 Newton is making. 8 Newton is making 30 degrees with the east. 30 degrees with the east, and the east is an horizontal direction. 30 degrees with the east.
that the last of them all is 12 Newton, and 12 Newton is making an angle of 45 degrees with the vertical. I hope you can see that while isolating them, I was taking each of them with their direction. I was showing them the way they are in the original diagram, because we are also going to need those directions, 45. So these are the vectors that I have from the board. These are the vectors that I have on the board so clearly. Now, we want to resolve each one of them. We want to try to resolve each one of them along their vertical and horizontal direction. Why are we using horizontal and vertical direction? Because those are the two common directions that everybody understands. We know what is vertical, we know what is horizontal. That does not mean that there are no other directions that we can resolve, but we are going to get things more complicated. So when you have questions like this to do, always think of vertical and horizontal direction. That is all. So what we are going to do is to resolve them. And please understand the way I said you can resolve very quickly. I'm going to complete the y component and the s component beside each one of them. I'm going to complete the y component and the s component beside each one of them. I'm going to draw the s component and the y component, and the s component beside them. Please note that all components were drawn from the point of origin of each of those vectors. I was not just drawing them from anywhere. I was drawing them from the point of origination of each of those vectors. Now remember that I also told you how to resolve. I said the component that is beside the angle is your cos when you are resolving along the vertical and horizontal component. The component beside the angle is your cos, the other component is your sine. If we apply that here, we will discover that this is 6 cos 30 because the vertical component is beside the angle. The other component is 6 sine 30. Here too, the component beside the angle in this case is the horizontal component, and it will be 8 cos 30, while the other component will be 8 sine 30. The component beside the angle here is the vertical component, and it will be 12 cos 45, while the other component is 12 sine 45. With that, I think I have resolved each one of them, except the first one. The question is, why did I not resolve 10? Because 10 is already vertical. And because it is vertical, it will have no horizontal component. Mind you, I said it earlier that every vector does not have any component in the direction that is making 90 degrees with it. If we are to find it, if we are to force it and find it, we'll get 10 cos 90. And 10 cos 90 is 0. Any vector will not have a component in the direction that is at 90 degrees to it. If it is horizontal, it will not have vertical component. If it is vertical, it will not have horizontal component. So if it is vertical, you treat it purely like vertical. If it is horizontal, you treat it purely like horizontal. Horizontal forces do not have vertical component. Horizontal vectors do not have vertical component. Vertical vectors of forces also do not also have horizontal component. So once you have a vector that is taking a direction either horizontal or vertical, I think those type of vectors have come to simplify your problem, since you are not really going to resolve them. Now, what I have, I'm going to proceed a step further. There are directions that are directly opposite each other. In that case, we must call one positive and we must call one negative. There are directions that are directly opposite each other. For example, the north is directly opposite the south. East is directly opposite the west. When we have those type of directions in a question, we try to attach sign to them to show that they are in opposite direction. We'll call one positive. I will call the direction that is directly behind it negative, for the purpose of simplification anyway. Now, what I advise students to do in that case is just use the same style that you always use on your graph. On your graph, you know that the upward y is your positive, the downward y is your negative, the right is your positive x, the left is your negative x. So any component that is along the north must be positive. Any vertical component that is along the south must be negative. Any horizontal component that is along the east is your positive. Any horizontal component that is along the west is your negative. If we do that with all of these that I have, you will see that each of them will have signs that we can attach to them. I hope you know that this is plus 10 because it is vertically upward. This is also plus. The components here are plus and minus. I don't need to attach component to the original vector. It is just its components along the y and x that I need to attach direction to. This is plus, sorry, because it's in the direction of our positive x. This is negative, is in the direction of our negative y. This is positive, is in the direction of our positive x. This is negative, is in the direction of our negative x. This is positive, it is downward, it's in the direction of our negative, is negative because it's in the direction of our negative y. So check, this is the south, south is negative, this is west, or you learn it like that, so depending on how you wish to do it. If you can learn it like east and north are positive, while your west and south are negative, you still get it that way. If you have done that, the next thing is to now form a table. You put your results in a table. You write the vectors, you write their x component, and you indicate also their y component. You can also write it as horizontal and vertical component, no problem. So we'll list out all the vectors that we have. We have 10 Newton, we have another that is 6 Newton, we have yet another that is 8 Newton, and we have the last one that is 12 Newton. Then we can fill it in. 10 does not have any s component. I think I told you earlier, it is vertical, it does not have any horizontal component. Its vertical component will be plus 10. 6 will not have any vertical, 6 has a vertical component, and the vertical component is 6 cos 630. Please, it is plus, while its horizontal component is 6 sin 30. For 8, the vertical component is minus the s component. Okay, sorry. We are filling the x and the y first. The s component here, 6 sin 60, while the y component is 6 cos 60. The s component for 8 is plus 8 cos 30, while the y component is minus 8 sin 30. The s component for 12 is minus 12 sin 45, while the y component will be minus 12 cos 45. I've left this small space beside them to evaluate each of these values. And add them together. 6 sin 60 is 6 multiplied by 0.866, 6 times 0.866, and our answer is 5.196. 8 cos 30 will be 8 cos 30 will be 6.928, while minus 12 sin 45 must be minus 8.485. So we'll do for the other side. 6 cos 60 will be 3, minus 8 sin 30 will be minus 4, while minus 12 cos 45 will be minus 8.485. That was easy for me to do because I understand that cos 45 and sin 45 are the same.
So I can now add all of this value. I will get a total x. I will add all of the values under y to get the total y also. So if I do that for x, I will have 0 plus 5.196 plus 6.928 plus minus 8.485. We have our answer, and that answer is 3.639 Newton. Our total y will be 10 plus 3 minus 4 minus 8.485. Our answer to that is 0.515. And so if we are asked to find what we have now are the x and y component of the resultant vector. What we are trying to find is the resultant vector. We have what has happened on the board now is we have been able to reduce the 4 vectors that we have to only 2, a total x and a total y. So if the question had asked us to find the s component of the resultant, the answer is 3.639. If the question had asked us to find the y component of the resultant, it is 0.515. These two are the component of the resultant. These two are what we are now going to use to find the resultant. So there are times that the question will not even want you to find the resultant. The question will just want you to find the s component of the resultant. That means after resolving everything, what is the total x that you have? The sum of the x, the result of all of the x. The answer is this. If the question had asked you to find the y component of the resultant, after resolving everything, what is the total y that you have? And this is it. So if we now want to find the real resultant from the component of that resultant, what we will do is we will draw the resultant again. The two components that we have, the y component, our final y component is positive, so we'll draw it in the direction of the positive. This is 3.639. The total y that we have is 0.515. It's 0.515 and it's also positive. 0.515 is 0.515. If this were to be negative, we will draw it downward. If this were to be negative, we'll draw it in the direction of the negative x. But that is what we have. So we'll now find the resultant. And what has happened is we have been able to reduce, like I said earlier, we have been able to reduce the 4 vectors to only 2. So we can now find the resultant of the 2. And the 2 that we have resolved them to are mutually perpendicular. They are making 90 degrees with each other. I have already told you how to find the resultant of 2 vectors that are at 90 degrees to each other. We'll use Pythagoras theorem, we'll use SOHCAHTOA, we'll complete the rectangle. How do we do that? We will copy 0.555 along y, we'll put it here, 515. Then we'll copy 3.639, we'll copy it and put it here, 3.639, I'll put it here. And then we can now find the resultant from their point of intersection. So the resultant, we can easily find it, since this is a rectangle, as 0.515 squared plus 3.639 squared. So the resultant squared must be equal to 0.515 squared, which is 0.515 all squared, and that is 0.265. 0.265 plus 3.639 squared. 3.639 squared is 13.242. So it means the resultant squared must be equal to 13.242 plus 0.265. Our answer is 13.507. If that is the case, it means the resultant will be square root of 13.507. We'll do the resultant square root of our answer square root of 13.507, and we have 3.675 Newton. That is the resultant of those problems, of the particular problems that we have been given. And remember that I said the magnitude of the resultant is not enough. You have to find the angle which will signify the direction of that vector. So I'm going to find the angle. This is theta. To find that theta, it means I will use tan theta is equal to, the opposite is 3.639 divided by the adjacent. The opposite is this in this triangle, and this is the adjacent, which is 0.515. So it means my theta must be arctan of 3.639 divided by 0.515. If I do that, I think I'm going to have arctan of 3.639 divided by 0.515. Our answer will be 81.944. 81.944. So I'm going to express the resultant that we have now as the magnitude 3.675 Newton at not 81.944 degree east, because it is the angle, that angle that I have is between the north and my east. So with that, I've come to the end of the solution to this problem, how to find, and that is what I want you to always do anytime you are looking for the resultant of vectors that are more than 2. This is the solution to the vector. We'll now move on to some practical applications of vectors, particularly as regards resolution and finding resultant of vectors. We are just going to try some questions that deals with the application of scalars and vector. The very first one that we are going to get to see here now is, from this question we are told that two forces whose resultant is 100 Newton are perpendicular to each other if one of them makes an angle of 60 degrees with the resultant. Calculate the magnitude. We have two vectors. The two of them are perpendicular to each other. So let me represent one with A and the other one with B. Two vectors that are perpendicular to each other, so they are making an angle of 90 degrees with each other. Their resultant is 100. Mind you, I hope you know how to get the resultant when two vectors are perpendicular to each other. That's the one that I said you are going to complete the triangle. I'm going to bring this A here, and I'm also going to bring this B here. So the resultant of the two must come from their point of intersection. That's the resultant. We are told in the question that the resultant is 100. Their resultant is 100. Their resultant is 100. They now said, if one of them, one of A or B, makes an angle of 60 degrees with the resultant, calculate its magnitude. One of them is making an angle of 60 degrees with the resultant. It could be A, it could be B or A that is making angle of 60 degrees with the resultant. Whichever one that you made to be making angle of 60 degrees with the resultant, find its resultant. So if I find its magnitude, if B is making 60 degrees with the resultant in this case, then what is B? If to you A is making 60 degrees with the resultant, what is A? That is all you need to find. And that is very simple to do. That is extremely simple to do. If I take this triangle, I'll get my problem solved from it. The adjacent, this is the opposite, I'm not giving. The adjacent is B, and the hypotenuse is given to be 100. Hypotenuse. So I know the adjacent, I want to find the adjacent, I've been given the hypotenuse and the angle. That looks like cos. So I'm going to say that cos 60 is equal to adjacent, that's B, all over the hypotenuse, 100. So B therefore should be equal to 100 cos 60. And 100 cos 60 must be 100 cos 60 must be 0.5. It means that B will be 50 Newton. And that is our final answer for this question. There are other questions that we can try there. We are told that a boy is pulling a load of 150 Newton with a string inclined at 30 degrees to the horizontal. There's a load. There's a load. The weight of that load is 150 Newton. We show weight of an object. The weight of an object, in case you don't know, the weight of an object is always shown vertically downward. Our weight wants us to go downward. The weight of an object is shown vertically downward, and that is 150 Newton. We are told that it is 150 Newton. So the next part of the question is that the boy is pulling the load of 150 Newton with a string inclined at angle 30 to the horizontal. There's a string. That string is inclined. That string is inclined. I hope you know how we draw inclined things. There's a string inclined at 30 degrees to the horizontal. The string is inclined at 30 degrees to the horizontal. The string is inclined at 30 degrees to the horizontal. 30 degrees to the horizontal. So I've shown the horizontal, and I've shown that the angle between the string, this line, this inclined line represents the string, because it said the string is inclined. And the string is also making 30 degrees to the horizontal. So we are now asked that if the tension in the string is 105, the tension is a force that acts along a string, and the tension is 105. The tension in the string is 105. So we are asked to find, this question wants us to find the force tending to lift the load off the ground. What is the force that is trying to lift the load from the ground? What is the force that is trying to lift the load off the ground? Now, the very first thing to do when you have an inclined vector in a question is to resolve it. When you resolve it, it is now possible that you have an idea of what you want. So I'm going to resolve that 105. I'm going to resolve it into the horizontal and the vertical. Mind you, I cannot resolve 150. 150 is already vertical. I don't need to resolve it. It is 105 that is inclined. It is only inclined vectors that you can resolve when you are solving questions on horizontal and vertical plane. And the horizontal vector is already the inclined vector is 105, so I'm going to resolve it. So I remember what we said about resolution. The component beside the angle is cos. The component beside the angle is cos, while the other component will be sine anytime you are resolving into horizontal and vertical. So this must be 105 cos 30, while this other one will be 105 sine 30. And if that is the case, then we can now solve it and we'll get the answer. What do they want us to find? They said once you resolve a vector, you really don't need the vector anymore. You have been able to break it down into two components. So the question wants us to find the force tending to lift the load off the ground. The only force in this diagram that is looking like it's going to lift anything is 105 sine 30. Definitely, if you push in this direction, you are not lifting. If there's any force in this direction, it's definitely not lifting. Lifting has to do with a vertical or upward exertion of a force. And the only force that is doing that is 105 sine 30. So that force that is tending to lift it off the ground is 105 sine 30. And 105 sine 30 will be 105 multiplied by 0.5. If you do that, you should have something that looks like 252.5 Newton. And that is our final answer to that question. Now we'll try to see more questions, like another one that I have. The resultant of two forces, x and y, will be greatest when the angle between x and y is 0. That's it. It is when the angle between x and y is 0. The resultant of two forces will be greatest when the angle between them is 0. Because it is when the angle between them is 0 that you get to add them. And I told you earlier that the resultant of two vectors, the maximum resultant that two vectors can give you is the sum of the two vectors. And when do we get to sum the vectors to get their resultants? When they are in the same direction. When they are in the same direction, what's the angle between them? It is 0. The least resultant of two vectors is their difference. And when do you get to solve their resultant as their difference? When they are in opposite direction. When they are in opposite direction, you subtract them. And when you subtract them, what you are going to get is the least resultant that you are going to have between them. And when they are in opposite direction also, the angle between them is 180. So they give you maximum when they are at 0. That means when they are in the same direction. They give you the least resultant when they are at 180, when they are in opposite direction. So that is also true for that. We will now take one more question and we'll round up this topic for the time. Now we are told here that a man can row at 6 kilometers per hour in still water and wants to cross a river to a position exactly opposite his starting point. If the river is 5 kilometers wide and is flowing at 4 kilometers per hour eastward, find the direction in which he must set off in order to accomplish his objective. How long will it take to cross the river? I will go over that again. We are told that a man can row at 6 kilometers per hour in still water and wants to cross a river to a position exactly opposite his starting point. If the river is 5 kilometers wide and it is flowing at 4 kilometers per hour eastward, find the direction in which he must set off in order to accomplish his objective. What we are going to do for this question is actually very simple. There are instances where we move in a direction, but because there is another current that is going either against us or in favor or in another direction, we find ourselves getting to a point where we have naturally not planned for. For example, if you have still water, like the one you have in a swimming pool has stagnant water, water is not moving in any direction. So if you decide to cross the pool and you move straight and you row straight, let's say you are moving with a boat, if you cross straight, if you maintain the straight path, you will find out that you are going to get to a point directly opposite where you have started. That is not the case when you are moving in a river, when you are rowing that same boat in a river. In a river, I expect you to know that there is a water current that is drifting the water in a particular direction. Let us assume that the water is moving in this direction. If they call it water, if they call it stream, if they call it river, or they call it stream, then it must move in a direction. If you decide to row from one edge of the river to the other, if you decide to row one edge of the river, and you are maintaining the same straight line that you have here, you will eventually find out that by the time you get to the other edge or bank of the river, you will have landed at a point that is not directly opposite where you started from, unlike in the pool. The reason for that is so easy to understand because as you decide to move up, the water current moves you in a direction. As you decide to move up, the water current moves you in a direction. As you decide to move up, the water current moves you in a direction. So while you think you are rowing straight, the water current is actually drifting you sideways. And that is what will make you land at a point that is completely different to the opposite end of the point you have started. So the question now is, if you now want to get to the point where you have started, if you want to row such that with your knowledge of the movement of the water, you still want to get to a point directly opposite where you have started, then you must not move straight. You will move in a direction that is inclined away from the direction of the motion of the water, such that as you move in this direction, you expect the water to take you back in line. As you move in this direction, you expect the water to take you back in line. As you move in that direction, you expect the water to take you back in line. Ultimately, if you calculate your angle very well, it is now possible that even despite the fact that you are trying to move in an inclined direction, you will eventually land at a point that is directly opposite where you have started. That problem, that illustration can be solved with the knowledge of vectors. And that is what we want to do with this particular question. So mind you, there are three things now generally involved. You wish to move straight, but because you know that the river is actually drifting in this direction, you now decide to row your boat in this direction. So when you decide to row your boat in this direction, you expect the river to take you back in line so that ultimately you will now have this velocity. Ultimately, you will now have this velocity. And that is what we want you to find. That is what the question here wants us to find. So when you have a problem like this will be referred to as your velocity in still water. This is how you will have moved if the water were to be still. This is the velocity with which you were moving, not disregarding the movement of the water. This is the velocity of the water itself. And this is now going to be the result of the two. This is going to be the velocity with which you will now move in the running water. This is the velocity with which you will now move in the running water. A combination of your velocity in this direction and the velocity of the water moving in this direction. That is what will now give us the velocity in the water as you are trying to move ahead. So let's go back to the question. We are told that the man can row at 6 kilometers per hour in still water. So his velocity in still water will be called the 6 kilometers per hour. We are also told that the river is flowing at 4 kilometers per hour eastward. 4 kilometers per hour eastward. So this is the velocity of the river. It's flowing at 4 kilometers per hour in the direction of the east. We are asked to find in which direction must it set off in order to get back in line. In which direction must it set off if he is now to move such that he will land at a point directly opposite where he's starting. So I'm just going to find this angle. I'm going to find that angle. Once I know that angle, that's the direction in which he must go. And it's so easy to know. I know the opposite to be 4 kilometers per hour. I know the hypotenuse, to be 6 kilometers per hour. So I can easily use sine. Sine theta is equal to, what is the opposite? 4. What is the hypotenuse? 6. So theta, therefore, must be equal to arc sine of 4 all over 6. And arc sine of 4 all over 6 must be 41.81. 41.81 degrees. So if he's to land at the opposite end, he must row the boat at 41.81. Because they mentioned the word east, I must express that angle in cardinal form. This is north, and this is the direction of my west. So if I'm going to go back in line, I must move in the direction north, 41.81 degrees west. That is it. But there's another question. They said, how long will it take to cross the river? Mind you, the width of the river is also given to us in the question. They said in the question that the width of the river is 5 kilometers. The river itself is 5 kilometers. So once I know the width of the river, I will know the velocity that the object, the body, the man is going to have in that direction. The velocity is going to have in that direction is this velocity. Because if the 5 is the width, is the distance from the bottom bank to the top bank of the river, then I must know the velocity also in that direction. And how will I get the velocity in this direction? I can use SOHCAHTOA to find it. I can also use Pythagoras theorem to find it. Since I know the hypotenuse here to be 6 and the one of opposite or adjacent to be 4. So I can easily do my V, my 6 squared, must be equal to 4 squared plus V squared. And V squared must be equal to 6 squared minus 4 squared. V squared must be equal to 36 minus 16. V squared must be equal to 20. My V must be equal to square root of 20. And square root of 20 should give us something within the range of 4.47. kilometers per hour. So I know the distance that he wants to travel, and I know the speed with which he's going to use to cross the river, 4.47 kilometers per hour. I can now find how long it's going to take him to cross that river. We know that speed is equal to distance all over time. If we make time the subject of the formula, we'll have speed divided by distance divided by speed, and the distance is 5 kilometers, while the speed is 4.47. If we divide them, we should have 5 divided by 4.47, and the answer should be 1.118 or 119 kilometers, no, 1.119 hours. Mind you, our distance is in kilometers, our speed is in kilometers per hour, so our time should be in hours. This is our final answer for this question, and with it we have been able to come to the end of the treatment of this topic, scalars and vectors. It's been an interesting time having to treat this topic with you. I hope you join us for another interesting package of another topic in physics. Thank you.